Good morning, class. Welcome to a continuation of our lectures on quantum mechanics. We'll just be discussing, for the first few minutes, we'll be discussing the finite square well. We will go through it quickly. Again, you have a finite square well. The potential is defined by this one. You have negative V sub O for this region, negative A to A. So this is the potential, and then beyond to the left, beyond negative A, you have zero potential, and then beyond A to the right has zero potential. So in this case, you can see that when you flip at the at y-axis, you can see that the potential is an even function. So when you flip here, when you flip on this axis, the potential would just be the same. So it's an even function. So here we can get the bound states as well as the scattering states. For the bound states, we check in the region x less than negative a here. We check that one, and then so in that case, your Schrodinger equation, since at this region the potential is zero, the Schrodinger time independent Schrodinger equation will just have this. And then of course you can transform that by letting kappa as equal to negative 2m as equal to square root of negative 2m over e over h bar. You can transform this into this equation. So the general solution in this case would be the wave function of this form. And the first term here, because this is going to the left direction, so if you go to negative infinity, this will become so large so that we have to, so that it's now it will now violate the requirements for wave functions. So this will go to infinity at negative infinity. So we have to set a equal to 0 so that our phi will now be this for the left side. For the right side also, we will just have this as a solution, because towards this side, going to the to positive infinity, it will also blow up. The term with e to the kappa x will blow up. So you'll only have this solution for x greater than a. For x less than a, this will be the solution. Now for here, we will get the wave function for that one. So for that region, you have Vx equals Vo, and then you will have this time independent. You will have this time independent Schrodinger equation. So by letting L equal to this equation can be transformed into this equation. And so you will have, since your particle here is bounded, so your particle moves in the boundary. So you will now use, instead of the exponential, you will now use this kinds of solution, sine and cosine. You will use that. And, of course, C and D are just constants. And by the way, looking at this potential, this is an even function. We can use either sine or cosine, but you will play a lot of sign changes, positive, negative, if you use sine function. But if you just use cosine, um, because this is already an even function, you will just uh, you will be able to play the signs, the positive, negative. Um, it's much more convenient to play with cosine than to do it with sine, um, because this is already an even function. So you can use sine here or just cosine. So we'll just look at the solutions. Um, say for x greater than a, or x greater than 0, to be this cosine. We can also do sine, but here you cannot write the other side into this function. You have to write this as negative phi x. So it's a, and here you cannot write also um, this one, because get uh, you have to get the sum uh, of this term, which is sine, and then this one would be that, and it's not good to work. It's so messy to work with sine. So let's just do this with cosine, since this is even and we have an even potential function. So let's do the cosine, so that we can write also for x less than 0, we can just write phi negative x. So for x less than 0, this would just be e to the kx, and this would just be uh, cosine cosine lx, the same, because cosine of theta is equal to cosine of negative theta. So looking back here, um, we're just going to specify the potential from here to here, and then if we just change the sign of x, then we can also get the solution for here. That's what it says for this solution. So now again, we have for the boundary, for the bounded solution, for the bound states, um, you have to deal with the continuity at the boundary, the continuity of phi at the boundary. So that's why um, you have to set at x equal to a. So this is now a. Your x is now a here. Is now a, and then that is of course equal to d cosine LA here. And the continuity of the derivative of phi with respect to ds. So if you get this derivative of this, would just be this one evaluated at a. So you have to change um, You have to change x with a so that you also uh, get the derivative of this with respect to x, and then evaluate that a also. So you will now have these two equations. Then you can divide this equation with this equation. So if you divide that, you can cancel f. And so you can cancel f and uh, exponential of negative ka, and then you can also cancel b and d, and then you will have this one. Now we will solve for E. What is the energy? So by the way, the kappa and L are both functions of E. So we can find the energy through L and K. So let's find that. So we let Z as equal to LA, which is just this one, and then ZO to be the lowest Z. ZO is the lowest Z, which is equal to A over H bar times 2M V sub O. Uh, you, you, you actually, um, you actually have this here. You set E equal to 0, so that you have the lowest. But this is 0. That's if you add E here, that would be L. So anyway, that's the lowest energy. You set these variables. So you will have you will have here tangent Z, tangent Z, this one, and K over L would just be square root of, this is K, or not K but kappa. Uh, Kappa over L. What is kappa? Kappa is, this is L and this is kappa. So kappa over L will just give you Z sub O over Z square minus 1 and the square root of that. So you have this equation, and this is a transcendental equation. You can, this means that um, this is satisfied by the graph of this and the graph of this, and you get the intersection. The equation is satisfied. So you can graph tan Z, you can graph tan Z or tangent of Z, and then you can also graph this. This is like a parabola, um, one-sided parabola. So you have that. So the intersections, are the points at which they're equal. So those points you can determine the energy. So these are the points you can determine the energy. There are two special cases. So you have these points. There are two special cases for wide, deep well. This means that if it is wide, the width of the well is large, and deep, the 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 potential is also large. V sub O is also large. This means that um, VO is large, and also VO is large, ZO is very large in this case. And A is also wide. So this is also large. So ZO is really large. So ZO is really large. Hmm, this one is very large. So what happens here? So the intersections just occur slightly below, for this case, slightly below pi over 2. So in this case, because if ZO is very large, this would be um, this would be this would be the curve would be like that, uh, slightly higher than this. Curve would be slightly higher than this, and so the curve would look like this. Wait, because it's too wide, the curve would look like that instead of this one, because it's now very wide. So you have to you have the curve to have to you let the curve to stretch out. So the intersection would occur on this Z. You have for Z1 you have here. For Z here doesn't have any intersection at this point, at this range, at this range of values, but here you have an intersection so that your n is always odd. So you will have Zn. Zn will now be this, and Zn will have Ln, and Ln will have En here, so that your energy will be um, approximately this. So here, um, E plus V is the energy above the bottom of the well, and on the right are precisely the infinite square well energies. For a well with 2A, by the way, this is the equation is way back in the previous lectures. So for the finite square well, uh, as V goes to infinity, there are only finitely many bound states that you can have. So um, for so you can only have like n. You can count that, because for very wide well, of course the ZO will have to touch the z-axis, and if it touches the z-axis, then the intersection will have to be terminated as it touches the z-axis, because if it touches the z-axis here, there will be no more intersection. So in this case you have 3, and if you go higher, if you go to a wider well, maybe you can have an intersection of 5, and then or 7, and then you have 9, for as long as n is an odd integer. So you will have those intersections. Now there's another special case, the shallow and narrow well. The shallow well has VO that is small, and for the narrow you have a very small also. small width, and then very shallow. And that means your ZO is very small. You can look at this. This is small, and this is also small. The ZO is decreasing. So in this case, um, so if you have a shallow well, you will have like a graph that is like that, and your Z would be um, very small. Um, hard to draw, but um, it has to touch the Z axis immediately, so that so that whatever happens for this so that whatever happens for a shallow well, there is always one intersection that could occur. So in that case, for shallow narrow well, as Z decreases, there are fewer and fewer bound states. There are fewer and fewer intersections until finally, for Z sub O less than pi over 2, which is here in this direction, in this region, um, the lowest odd state where the lowest odd state disappears, only one state remains, and that state is and that state will have the energy equal to um, equal to will have the energy equal to this. Uh, the energy would be um, associated with this. So the energy would be zero, um, um, but the potential energy remains for that region. So let's now again, I can tell you that you can um, normalize the phi here for the bound state. You can normalize this. You can get normalize, meaning you can get F and D. And of course, to normalize this, you have to integrate phi star phi dx. So that's about, of course, the square well. Um, we'll now go to, that's about the bound state. Let's now go to the scattering states where energy is greater than zero. To the left, where Vx is equal to zero gives this one uh, for this region, for this region, um, for this region, and for this region, um, we set that. Um, so for that region, you have an incident. For scattering state, you have an incident wave function, and then you have a reflected wave function. And here you can, as usual, you have k is equal to square root of 2m over the square root of 2m e over h bar. So for this region, for this the middle region, for the middle region in the scattering states, you will have this solution again, where L is equal to that as usual. And then for the right, x greater than a, x greater than a here, we the solution would have been f exponential of negative ikx plus g to the ikx, but uh, we do not we do not uh, we do not let any wave coming from here. We in the usual scattering experiment, you have an incident wave, the transmitted wave, and then um, you have the reflected wave and the incident wave there, going there, and then it's going here, and then it's going there. Incident, transmitted, and reflected. So that your G will be equal to 0. You only have this as a transmission, as a transmitted wave. Then we impose again boundary conditions phi and d phi dx. Um, they should be continuous at negative a and positive a, so that again um, so that you will have this expression, because here you have this, you set equal to negative a, and then you will have that, and this must be continuous with this one at the boundary. It must be continuous with this one at the boundary, so that you will have this. And then the derivative of phi with respect to this at negative a would also have to be continuous, so that you will have this as equal to the derivative of this with respect to x evaluated at a. So these are now equal. And then phi x would also have to be continuous at x plus at positive a. So this one is so this one is the expression that's going to be derived. And the continuity at positive a also of the derivative of phi with respect to x. So you have to. I need your consent on it. You want us to continue. So you also have to get the derivative of this and then the derivative of this to get this expression. You have to evaluate at x equal to positive a. So there are 4 boundary conditions. You can follow the details. You can write the details on your own, and then with this you can eliminate C and D, and you can solve for V and F, which are these are the important quantities. C and D are just arbitrary constant. They can be eliminated. This one you can eliminate this by the boundary conditions given by these 4 equations, so that you will be able to find B equal to this and this one. So in this case, what is F over A? You can square this, you can square that, and then you can also get the complex conjugate of this and then square. So your F of A, your F divided by A square, this will just be equal to F conjugate times F, and the denominator is also A conjugate over A. But anyway, they will just be F over A squared, F squared over A squared. So you'll be getting this expression for um, your transmission um, coefficient. For your reflection coefficient, that would be F over B. F over B. So you have to just have to square this and square that. So um, you'll be you'll be no, this is A B over A, sorry, B over A. So the transmission coefficient will just be B over A here. Wait, let's look at the B over A. So it's in this case you have to in this case you have to write F here in terms of A. So replace this F with this. You have to replace that. And then you divide B over A, then square, you will have the reflection coefficient, the R. This is the transmission coefficient. The transmission coefficient is the contribution or the part of the incident wave that passes through the potential, and the reflective coefficient is the part of the incident wave that is reflected by the potential. So you can get B. I mean R also. So at T equals 1, what does this mean? T equals 1. This means that all the incident wave um, passed through the barrier. That means the well becomes transparent. It means that all the wave function passed through the barrier. So there's no reflection. If uh, if this one, what happens uh, if T equals 1, this one would have to be 0 if T equals 1. If this is 0, everything here, if this is 0, if this one is equal to 0, everything here will be 0, and your T is equal to 1. That means all the wave passed through. If that is 0, then this must be a multiple of n pi. That is multiple of n pi. And so your energies, if you transform this, you can get your energies to be equal to that. Or En is equal to n squared pi squared h bar squared over 2m times 2a squared minus v sub o. That's your En. So this is the energy for perfect transmission, meaning all the incident waves went out of the barrier or have passed through the barrier. So this is the energy. Now for the scattering matrix, I hope that's the end of the finite square well. Then we'll go to the scattering matrix. This is important also. So if you have any wave or wave packet that or any potential, and then you have a wave packet here or a wave or any wave function going to here. Some of this wave in general, some of this wave um, will be reflected, and some of them will be transmitted. There's also another wave coming from here, and some of this wave will have to be added to the transmitted wave from A. We're going to here, and some of this wave will pass through, and they will be added to this wave. So if you look at this um, figure, um, for region 1, in this region, the potential is 0. So you have this solution. You have this solution. And for this region, you will have this solution also. You have that solution, where k is equal to 2m over e. As usual, k is equal to square root of 2m over e. For region 2, we don't have a specific potential here. Let's consider an arbitrary potential, which is just a sum of this potential and this potential. The c here are arbitrary constants. Now, with the boundary conditions, uh, doing these boundary conditions again, doing these boundary conditions that we have at some boundary, we can eliminate C and D in this case. We can eliminate C and D, and we'll be able to solve B, and of course we can solve F. We can solve F and B, where in this case, the G, in the usual scattering experiment, the G is now not 0. So we generalize that the G is not 0, but we can just set, we can set G equal to 0 if we have a specific case where there's no wave coming from the right. So we can set G equal to 0. But in this case, we allow G to come. We allow two incident waves, two incident wave functions. So with this, there's a scattering matrix that can be formed, such that you can write this matrix as S, equivalent to this, and you can write B in terms of the elements of the matrix. So this one. What are these elements? So they form a 2 by 2 square matrix. So that's it. And then of course, you can get the reflective coefficient, the reflection coefficient. This is of course B over A. You set G is equal to 0. And this is equal to S11. And F over A, F squared over A squared, set G is equal to 0. This is also the transmission from the left wave function. And this is equal to S21. So that's what you have to put in this matrix. So in this case, um, this is an element of the S matrix, or this is also an element of the S matrix. Here, um, let's look at. These are also elements of the, this is S11 and this is S12 in this case. Where, but G is, in this case, is equal to 0. So anyway, you have S11 and S21. I'm sorry, not S12. Um, for the right, wave coming from the right, where G is now not 0, but you have to set A is equal to 0. And these are also the elements of the matrix. So that's how you get the, that's how you get the elements of this matrix. And these are, it looks so simple with with this expression, but it's actually, each of these elements are complicated, and complicated expressions. Not really complicated if you have the patience to solve them, but looking at the expression, they're a kind of really messy expressions. So you are uh, you are looking at the scattering matrix, but you can also get out of the scattering matrix. You can also get the bound states of this. You can also get the bound states of this situation. You just have to. So if you have the S matrix, that is for the scattering states. Um, Here, I'll just read this statement. The S matrix tells you everything there is to know about scattering from a localized potential. It also contains information about the bound states, if there are any. Um, how do we know the bound states? This is the condition for the bound states. So again, F has this form for region 1. For region 1, we have that. For region 2, we have this, and then for region 3, we have that. So again, with kappa equal to that, this is for the bound state. For the scattering state, this is K, and this is positive for the scattering state. For the bound state, this is negative for the bound state. So the boundary conditions are the same as before. So the S matrix has the same structure, only that E is negative. In this case, E is negative. That's why you have the negative sign here. E is negative. So you have to change kappa into ik. This is not I kappa, but ik. And this time, you have to set A and G equal to 0 for the bound states. And of course, B and F are not 0. So this equation will give you only will give you uh, will give you only 2 elements, because this one is 0. This one, uh, for the other one of which is 0. Either A is 0, then you have G, or G is 0, then you have A. So that for example, for the finite square well, this is the S21. What is S21? This is F over A. F F squared over A. and this is just um, this one. So if you transform it, you have an S21 which is equal to this. If you substitute kappa to ik, S12 blows up. S12 blows up whenever you have this condition. So if this is the condition, then it will blow up. This one will blow up. This will go to infinity. That condition, that blowing up, will give you the bound state, because this is for the um, scattering state. And if this element will blow up, then that gives you the energy for the bound state. So if you use this trigonometric identity, you will find out that um, the tangent LA will just be L over K, and cotangent LA will just be negative kappa over L. This is L over kappa. So these are the conditions at which S12 and S21, this will blow up at cotangent to LA, and S12, which is the other element, will blow up at tangent to LA. Or a tangent L over K, I mean. So these are the conditions for the bound states of the finite square well. So that is the end of chapter 2. So next meeting we'll start with chapter 3, but I will solve some on the weekend. I will solve some sample problems, and I'll post it to our Google Classroom and also our uh, Mole room, uh, so that you can also review, and then we'll have an interaction session next week. So I hope the three of you will be there, will be able to participate in the interaction session. So that's all for now. I hope you've learned something. I'll put the link in our rooms, and you can then review the lessons, the lectures. So for anything, you can just put your questions or other queries there. That's all. Have a nice day.